Hello everyone, good evening. I hope I am audible. Can anyone just confirm? Hello.
Yes, sir, you are audible.
Yeah, thanks for confirming. We'll start with our session today. So this is our second week regarding the evolutionary computation for single and multi-object optimization. Let's quickly start with a recap of what was covered in the previous last couple of weeks in the lecture, as well as we'll also go through some of the problems that will be helpful for your assignments. The first week of lecture starts with a basic definition of search and optimization. Essentially, we discuss about what are the various decision variables. Examples, some of the, if say consider you have a problem of minimizing the time you require to move from place A to place B. Decision variables are essentially the ones that are under your control that you can vary, say your speed or mode of transport. It is those kind of variables. And second comes the objective function, which is essentially your total time taken to travel from point A to point B. And then you have something called constraints, which are essentially the boundaries of your search space. So consider you have some decision variables. With that, if you constructed an imaginary space, the boundaries of that space are essentially governed by these constraints. So these are, you can kind of say, the limitations upon the values that the possible decision variables can take. And then the lecture also talks about some of the practical problems that we encountered during optimization, essentially the ones we already know from our earlier subjects, that if you have any function f of x, you can identify the minimum or maximum of it by just doing del f by del x. So, but in general, practical problems usually have functions which are not differentiable. That is one of the problems which we frequently encounter. The same happens with constraint functions which are non-differentiable. And then we also have something called discrete search space. It's essentially the variables like the f of x. The x is not continuous. Say consider the previous example. If you want to move from point A to point B, you cannot move over all possible routes. There are only specific routes which you can take. And this is what we meant by discretizing the search space. And then you have something called mixed variables, which essentially means you have both continuous as well as discrete variables. And then the frequently encountered problem is the large dimensionality, where you have a lot of variables for your problem. And then you have something called nonlinear constraints, which essentially means the constraint depend upon the decision variables you have chosen. Like for example, if you consider the previous one, your constraint of road depends upon the time of the day. Say on particular times, some roads might be busy while the others are not. So while you're trying to minimize your total time, you have to consider these constraints which change dynamically over the time. Such type of constraints are called the nonlinear constraints. And then we also discussed about multimodal functions. These are essentially the functions which have a lot of local optima. Essentially, there are several local minima and then there exists a global optima. Such kind of functions are called multimodal functions. The challenge with such type of functions is essentially in finding out where exactly is your del f by del x 0. If you consider the standard case where del f del x equal to 0, you have several possible solutions. Out of this, you need to search from one solution to the next to identify which of these is the global minima again. And then comes the multiple objectives. These are essentially like you have 2 or 3 competing objectives. Say consider in the previous case, you want to minimize the time travel from point A to point B. At the same time, you want to minimize your fuel consumption, which are kind of competing in the sense, if you want to minimize the time, you need to move at a much faster rate and might possibly lead to more fuel consumption. So these are the kinds of objective functions which we usually encounter in practice. And then you have something called uncertainties in the variables, say estimation of traffic, which you could not know ahead of time. And then the computational expense is basically the amount of resources, computational resources you need to put to solve the problem on a computer. And then you have this multidisciplinary aspect, which is essentially because you have 2 or 3 different fields. For example, consider the previous traffic problem. You need to know about the network flows in the sense where the traffics are there, how the vehicles move. You need to know about GPS and all that stuff to be able to solve such kind of problems. After this, we also discussed about the problem formulation for this kind of setups, where it's kind of mathematically defining this in a more formal way. So we just told x is our variable. X is essentially the variable of, it can be a vector which has several variables, say like the routes you have to take, or maybe if you consider a general optimization problem of optimizing the design of some particular aircraft or something, X can be something like you need to have the material properties and then you may have something like the dimensions. All these parameters will come under x. F of x is essentially you call your objective function. This is a function that you ultimately want to minimize or maximize. In this particular case, we will just look about minimizing the functions. We will look at how to deal with maximizing in the next few slides. So if you want to minimize this function f of x, it's like you need to minimize your total costs. That could be one of your optimization function, or maybe in space graphs you need to minimize your total weights. This is that objective function which we want at the final step. And then we have something called the inequality constraints. These are the type of constraints, say inequality constraints are essentially the type of constraints which we usually encounter. Say in thermodynamics you have something called the entropy law, where the entropy always increases with time in a process. So these are such kind of constraints. There are many other constraints in engineering practice as well. And then you have something called equality constraints, which you essentially want them to be zero. These are the kind of hard constraints, say kind of mass conservation that you need to maintain in an engineering system. Usually we prefer to kind of limit these number of constraints because these are computationally difficult to solve. And then you have called the variation bounds. These are essentially some of the parameters which you have some physical bounds. Say for example you have a mass. Mass cannot be negative. Usually they tend to be always positive. So that is one kind of bounds on the mass. If you can have dimensions where you can say some particular aircraft wing dimension is between this range and this range. Too lower values and too high values are not acceptable. These kinds of bounds are called variable bounds. You can as well pose this problem in a different way, like the variable bounds can also be kind of stated as inequality constraints. We usually treat variable bounds in a different way, which we will discuss in a few slides. Yeah, the previous one which we discussed, where you want to minimize some function, but what else? Suppose you want to maximize your profit. How do you change the function in such a way? Like the same algorithm which we designed previously for the minimizing works for the maximizing as well. That is where we use this duality principle. So you have some small f of x and then you have a capital F of x. Minimizing small f of x is equal to maximizing capital F of x if capital F of x is negative of small f of x. This is a simple rule we use. You just take the function which you are previously defined for maximization, put a minus over it, and you solve the problem using the same algorithm designed for minimization approach. Now we'll look at the algorithm used for these evolutionary computation techniques. The first one talks about solution representation. This is essentially the way you tell the computer that how the variables have to be stored and how you have to operate on them. And then you start with generations. For each generation, what you are going to do is, if you happen to see the first step, it's like you initialize a random population, which is you call the parent population, and then you kind of evaluate a fitness. Fitness is essentially kind of objective function. It's kind of a function which tells you how the solution fits to the given objective function and the set of possible constraints. And the next what you do is a selection operator. Selection essentially is like when you have the several possible solution, it's a kind of a filter that tells you which of these solutions are fit to go to the next generation. Once you select the solutions, then you pass them through a variation operator. Variation operator essentially has two components to it, like a crossover and a mutation operator. You can think of crossover as exploring the search space. It's like finding all possible, it's like say you have to climb a mountain. Crossover is like you are kind of moving the mountain in various possible directions to identify which of the paths can lead to your aim of reaching the summit. Mutation is a kind of exploitation. It's in the sense, if you just do crossover, you might end up in some of the local optima. So you just kind of have some other kind of a way. We will look at how exactly mutation does this in the following slides. Once you have done the variation, you come up with the offsprings. Then you again pass them through a survivor. Survivor is basically kind of selecting the best possible solutions from the given pool of parent as well as offspring that could be sent to the next generation. And this loop keeps on repeating till the maximum number of generations is achieved. Or maybe in some of the practical scenarios, if your objective function say is weight, and you know like the minimum weight, if a weight of say 100 kilograms is sufficient for you economically, then maybe you can stop when your particular algorithm reaches 100 kilograms. that could be another stopping criteria. That depends upon your area of application. The second week of lectures starts with discussing about the binary coded generic algorithm. If we consider the previous algorithm we discussed, in this, the first step where you kind of represent the solution, this is where the binary coded generic binary coding is done. It's basically how you represent your parameters and how you to the computer. So the first step, genetics, is essentially what we call encoding the information. If you kind of take an analogy with your biological systems, it's there is something called a genotype and something called a phenotype. Genotype is the way in which the actual information is encoded in the chromosomes, and phenotype is the final observable characteristic at R level. In our course, we will discuss about something called all these real variables are encoded in the form of binary strings of a given length L. So in the last week, we discussed about some of the formula regarding how to encode this. So we'll quickly go through the formulas. We have something called a precision. This is essentially saying how much precision you want in a particular variable, to what decimal place you need that variable to be accurate. This is given by this particular formula, where you can see the numerator is essentially the range of your particular variable. The x of u is basically your upper limit and x of L is your lower limit. Well, the denominator is essentially 2 power L minus 1. That essentially comes down to saying L is your length of chromosome. Just to put things in perspective, say you have xl and xu. This is the domain of the particular variable, and what we are trying to do is map this particular range to another range which kind of varies between 0 to 2 power L minus 1. This mapping is essentially is what we are trying to do. Once you do that particular mapping, this is what you come up with. So if you have some particular variable x in the original map, original domain, you want to convert it into domain from 0 to 2 power L minus 1. Yeah, sorry. Yeah. The decoded value will kind of convert it into our domain. Say for example, let's consider one example of, say you have a value of x equal to say 8, and the limits of x are from 2 less than or equal to x less than or equal to 8, and you are, say for example, choosing a chromosome of length say 4. How do you find the decoder value for this particular example? Is you essentially use this formula. So if you can see over the numerator here, for L equal to 4, we have 15 possible combinations. It's from 0 to 15, and then you have x minus xl is basically your 8 minus 2, that is 6, divided by your total range 6. This comes down to a value of 15. So the decoded value is 15. So instead of actually converting this 8 to binary number, we convert 15 to binary number. So when you convert 15 to binary, you get something like 0 1 1 1. We have a chromosomal length of 4, and here you have the 4 bits for that particular string. So the essence here is the one which we discussed previously about the variation bounds. So variation bounds are treated in this particular way. So we are, when you are encoding that particular information, you are kind of converting it from the original variable bound domain to 0 to 2 power L minus 1. So if you would have done in a different way, where you kind of formulated your problem without variational bounds and kind of converted them into inequality constraint, then you would have to change this formula a little bit. For the sake of this course, we'll stick to this particular formula. Now if you happen to see something here, we discussed previously, when you kind of convert the original domain of 2 to 8, which essentially is a range of 6, now it is converted to 0 to 15, so that is essentially 15. So now you have a precision of 6 over 15. approximately around 0.4. This is what we meant by discrete search space. So now instead of 2 to 8, now we are having something called 2, 2.4, again 2.8. So we don't have anything in between. So by choosing this particular type of encoding, we are essentially kind of discretizing our search space, which may not be, which is a kind of a limitation, which we will be discussing in the coming slides, how to overcome this particular limitation or how you can essentially increase your precision. One way to, by looking at this, you can directly increase precision by increasing the value of L. So if you can have a chromosome of or a string of much larger length, you are essentially having a much larger, like you are having a lower precision. But this comes at a computation expense. If you increase your chromosomal length, you are kind of essentially increasing your computational cost. We will look at some other type of encoding algorithms to kind of deal with this. Once we are done with the encoding, the next step in the algorithm is essentially about the selection operators. Selection operators are kind of filters that tells you out of the given population, out of the solutions in the given population, which ones I have to choose. How will I know which ones I have to choose? Essentially, we talk about the two types of selections. One is a tournament, another one is a fitness proportionate selection. We will start with the tournament selection. So in tournament selection, essentially you have some population. Consider all these dots as possible solutions for that particular objective function we are trying to solve. The size of dot kind of indicates it's the relative fitness. Like a size having a larger dot is kind of having much larger objective function, while the smaller dots are having smaller objective functions. So our objective is finally to kind of find that particular dot which has the smaller size. So how do we go about it? The first step in tournament selection is to randomly pick, okay, before that, you have different kinds of tournament selection. In the sense, in this particular example, we are looking at only picking two individuals. It is called a binary tournament selection. Alternatively, you can kind of choose any 3 or 4, or you can choose per se any, say, K tournament selection. K tournament selection is essentially you pick K individuals from the population. For this particular example, we will stick to number 2 individuals. So say we pick these 2 individuals. After picking the individuals, what we essentially do is to compare the selected individuals. How do we compare them? We need to have some sort of metric to compare both of them. This metric is essentially what we called before as the fitness function. Fitness function should take into account both the value of objective function as well as your constraints. So say some particular function has a very low objective function, but it is not satisfying the constraints. Say the ones which you encounter usually in practice might be like you design one particular system and your objective function is to minimize the weight of the system, but then you cannot reduce the you cannot reduce the weight at the cost of reducing its quality or say its structural rigidity. So while you are evaluating your objective function, your constraints should also be taken into account. So a material with very low weight and low structural rigidity should not be the outcome of your optimization. So the constraints you set should be like some of the limits on, say, this is the minimum structural rigidity I require from that particular material. So that things have to be compared, have to be put into the function in mathematical way. Once you put them in a particular format, what we essentially do is to compare them. Once you compare, you will get to know, okay, this is the minimum. So this is what tournament selection does. You just take 2 individuals from the population, compare them with an appropriate metric designed for the particular problem of your choice, and then you come up with what is minimum. Okay, this particular example says minimum, but say you have a problem where you want to kind of come up with a solution which maximizes some particular function, then you kind of select the other one. You select this particular solution, the maximum solution, and you go ahead. So depending on your application, you can kind of select which one to choose. Now we are done with tournament selection. The next possible kind of selection operator is a fitness proportionate selection. To explain this particular example, this particular technique, we'll go through one example. Say you have a population of 4 individuals, and these are the fitness values of those individuals. So the first step is we just construct one table like this, where you kind of have the index is essentially kind of what are the individual solutions, and fitness is basically the function which is kind of a combination of both the objective as well as the constraints, and then we have something called Pi and Hi. PI is essentially, you can treat this as a kind of probability. It is more in the sense of saying how the particular fitness of that individual compares to the overall fitness of the population. So you can see PI is essentially the ratio of Fi by sigma Fi. Sigma Fi is the total fitness of the entire population, the summation of the fitnesses of every individual in the population. And then you have something called HI. HI is a kind of a cumulative probability which we will see how to calculate. So the first step is to calculate sigma Fi. You just do a summation over all the fitness present in the solution, and then what you essentially do is to kind of divide the fitness of that particular individual by this summation, and you populate the table. This is what you get. Say for the first example, what we do is 52 by 243. That comes around 0.21. So that is what we have here, and we kind of repeat it for all the next coming steps. Once you are done with PI, next step is to calculate HI. For the first individual, for the first index, HI is kind of equal to PI when I equal to 1. So you just populate the same, you just copy the same from PI. The next step is essentially to have a combination of both the top and the left columns, which is kind of PI plus HI minus 1. This is a cumulative probability. You come up with the same, you just kind of repeat it step by step to fill the entire table. You come up with these numbers. So you can see essentially the bottom number should always be 1. Just the sake that all possible combinations, like summation of all possible fitnesses, should be equal to 1. Now the next step is essentially kind of how do we select the individuals. Now we have these particular individuals. How do I go about selecting them for the next popular? How will I know which one of them is fit? Which one of them to select? Which one of them to select that would be going into the mating pool? What could be the strategy for choosing these individuals? The idea behind this is essentially any individual with a higher fitness value should be more likely to get selected. We are not directly selecting the individual with the maximum value. Say if you consider this population, the one with the maximum fitness is the fourth individual, 120. It has a fitness of 120. So if our objective is to maximize the function, you can right away select this 4, but then that is not our objective. We are not directly selecting in that way. We want this to be selected more likely, but not always. The idea behind this is to introduce stochasticity into the algorithm. The main advantage with this kind of approach is you will not get trapped in one of the local optima. So this will kind of ensure you that you will reach one of the global optimas. So we will see how this is done now. Now we consider this particular cumulative probabilities. So we will see. We'll consider one just to see how these values are on a scale of 0 to 1. We have 0.21, 0.47 and 0.51. Just to have a better picture, we'll see in this particular column. So you can see here, these are the values which we are referring previously, like we have 0s, 0.21, 0.47, 0.51 and 1. So if you can see here, each one of the area colored with a different color, highlighted in a different color, represents to one particular problem. So if you consider 0 to 0.21, you can kind of assign it to 1, the first individual. 0.21 to 0.47, you can assign it to the second individual. Similarly, you can do for the third and fourth. If you can see something here, so if this is my entire region, you can see 4 with higher fitness has much larger area compared to the other individuals, and 3 which has the lowest function value has kind of a very small area. Now, if I were to pick points, like generate 4 random numbers from this particular region, what would happen? Say my first point would be picked somewhere here, my second point would be picked somewhere over there, third point would be somewhere over here, fourth point would be somewhere over here. If you can see something like this, you see that when you try to pick from this region, you will be more likely to pick from regions having regions of region 4. That is essentially because 4 has much larger area. It's like saying you have a certain class with a certain number of students of, say, wearing a white shirt, say around 10 students, and a black shirt wearing 2 students. You will essentially probably end up, if you're kind of, when you want to randomly choose, say, 4 individuals from the population of, say, 12 members with 10 white shirts and 2 black shirts, you will more probably end up in selecting white ones. This is also similar to that particular case. So these are my solutions. It's like you essentially select 4 twice, 2 once, and 1 once. So these will go to the next generation. just to point out previously, like in this particular type of selection, you are kind of only selecting the ones which have maximum fitness. So this particular selection operator only works for maximization problems, and if when you are applying to minimization, care should be taken that you use the duality principle to kind of convert the minimization to maximization and then apply the algorithm. The next operation we will be dealing with is a crossover operator. Last time we discussed about two of them, like a single point crossover and a 2-point crossover. We'll quickly go through this. The first one is a single point crossover. The main purpose of a crossover is to kind of explore the search space. So in a single point crossover, let's consider two parent individuals with the following chromosomes. What you essentially want, the steps involved are basically, the first step is to decide whether or not to perform a crossover. When you have two parent individuals, you just don't want to do the exchange information between both the chromosomes all the time. You want to do it stochastically. So you will do it only with a certain probability. How will you go about doing that? First you need to have a random number generator. You can kind of, if you are familiar with any programming languages, you have some default function to kind of generate random number, or if you are using Excel or Google Sheets or Google or any other spreadsheet software, you can kind of use the default function to generate random numbers. You generate from a sequence called a uniform random number from the distribution of uniform random numbers. Once you generate the random number, what you essentially do is to compare it with something called the crossover probability. This crossover probability is some parameter that will be set by us, in the sense the user. The user has to set this crossover probability. Usually these will be set to a very higher value to kind of indicate that most likely you want to explore your search space. As and when the random variable you generated is less than or equal to PC, you have to perform the crossover. If not, then you just pass the whatever have been input solutions directly to the next generation. Once you have decided whether or not to perform crossover, so it is decided that we will perform crossover. Now what you will do? The next step is to kind of identify the site where you want to apply this operation. How do we do it? You just randomly select a site. Say if your chromosomal length is 4, you randomly generate a number from 1 to 4, a uniform distribution of 1 to 4, which can be done with any of the commercial packages, or you can also use any open source package to generate a random number between 1 and 4. If your chromosome number, the previous case of we have taken a much larger string, so if you happen to see over here, the string here has a length of 8, so we generate a random number from 1 to 8, and from, say we got a number of say 5. What do we do next? Okay, now once we have decided, we have chosen the site to where to perform the crossover, and then we'll actually do the crossover. How do we do it? Is essentially we take the two strings. Now we know we need to split at the 5th site, so we just split it at the fifth place. Now we have two different things. So what we essentially do next is just exchange both of them. Just exchange the tails of both of them. This is what you get. This is the end result of your single point crossover. Now we are done with single point. We'll just go to a 2-point crossover. In a 2-point crossover, it's just slightly different in the way, like instead of selecting one site, you just select two random sites. Previous example, we just took site number 5. We can actually take two sites, say for example 2nd and the 6th ones. So we choose two particular places. Now what we, in the previous case, we kind of exchange the tails. In this particular scenario, what we do is like there are different strategies. One strategy could be kind of selecting the middle ones and exchanging both of them. There could be other strategies where you kind of flip a coin for each set. Say for this particular set, you flip a coin. Say you get heads, then you exchange them. If you get a tails, you do not exchange. Again, you go to the next set. Again, you flip a coin. You get heads, then you exchange. Otherwise, you do not. It could be one way of doing. The other way could be you select both individuals and just exchange both of them. Exchange only the middle parts, leave the end parts unchanged. Which strategy to use depends upon the problem of application. Yeah, you have any question?
No, please. I just missed it.
Okay, fine.
Hello.
Yeah.
You have told about single point and 2-point crossover.
Yes.
Which one will be better? Is single point crossover is sufficient in most of the problem?
Yeah, we'll see it in this particular way. Say suppose you have a problem of 2 or 3 dimensions. Say you have 3 variables, x1, x2, x3. And your function, your objective function in a kind of depends on all these variables in significantly. Like even if you change x2 or x3, it's kind of highly sensitive to all these parameters. Then when you have a chromosome of particular like this, where only the first 2 bits represent x1, second 2 bits represent x2, the next one represent x3. If you would like to do single point crossover, what would essentially happen is like you would be ending up changing only one of these variables. Like if you see here, now by exchanging these two, only x2 will get changed here. But this is for this particular choice of your random sites. Say you can also choose some other random sites. Say you have these 2 variables.
But this sensitivity of the variable is already taken care of by choosing their length. For example, x1, if it is less sensitive, then I can take it 4 bit. x2 if is more sensitive, I can take 6 bit like that.
No, that is precision. Precision is kind of a different aspect. So when you're kind of having a more length, it's like you will get more decimal. You will be accurate up to more decimal places. Sensitivity in the sense, to give you an example, say you have a function y equal to x and y equal to x square. So for a given, like for unit change of x, how much your y will change? X square is kind of more sensitive than y equal to x, right?
Yes.
So this is what I'm, by sensitivity, this is what I mean. Yeah. So if you have something like this and you have chosen some random split like this in a single point crossover, so your first 2 bits is x1, the next ones are x2, the last 2 are x3. Then by this particular kind of split, when you are exchanging the information, you are kind of, one of them will be unchanged, the other variables will change. Like x2 and x3 here, x2 and x3 are kind of getting interchanged. But x1 is just remaining as it is. But if you do a 2-point crossover, say here, you can see like x3 will remain unchanged, only x2 will change. So in the second case, it's more like you're kind of changing only one by one. Like you will change x2, then at some point of time you will later change x3. So it will be like the rate of convergence might be slower than the previous one instead of doing the single point crossover. But that again depends on your application. Like if your function is not sensitive, or say if your function is sensitive to only x1 and other 2, it's not that sensitive. Sorry? So I think you got it right.
Yes.
Yeah. Now this is about a crossover, 2-point crossover, but instead you can actually choose a multi-point crossover. Basically, why do you have to limit to just number 2? You can actually choose 3 points, 4 points, 5 points. If you have even a much larger dimension, then you can kind of choose even more crossovers. But you have to just try it out. These are something called the parameters that you need to tune so that your convergence rate depends upon again on your computational resources you have. Depending on your limitations, you kind of choose, okay, this much computation is what I can do. You just go with that, and you also have your entire time for convergence. Your final solution will not be affected, but the time taken to reach the solution might get changed. The next operator is your mutation operator. So we discussed about 2 types of operators, basically local and a global mutation operator. We'll just look at one by one. Consider this particular binary string. Now mutation is basically to ensure that there is enough diversity in the population. So when you do essentially crossover, you are kind of taking 2 individuals and kind of exchanging information between them and coming up with 2 other solutions. So when you do this kind of steps, you are kind of exploring your search space, like you are kind of expanding your search space. What you do in mutation is kind of mutation, as you can just see some general cases, it's a kind of a random event where you have a sudden significant change in one of the bits. Local mutation is like when you have the entire binary string, you don't exchange information with any other. You just take one individual, and what you do, you change one of these bits. Like, you just go through this. The first step is similar to crossover. You have to decide whether or not to perform mutation. That you do in the same steps. You just have a random number generator. You generate one random number. and then you come up with something called, you compare this with your probability for mutation. This probability for mutation is again your kind of parameter in your design. So usually when we set in the crossover case, the probability is set to a very high number, but in mutation you kind of want to set it to a lower number. So you can think of it this way. Mutation kind of introduces drastic changes in your population. So if you have kept the probability of mutation very high, what can happen is as your solution is getting trained, as you are running your optimization, you might be having so many oscillations. So it's like, if this is your generations versus this is your objective function, what might happen is like you want to reduce your objective function, but then it might decrease and then increase suddenly because of mutation and then again decrease. So these kind of oscillations you might get if you put the value of if you keep the value of PM value to be very high. So it's again it depends on the problem, it depends on the sensitivity. So you need to tweak around these values to identify which particular value of PM will give you solution in a much smoother fashion. Once you are done with selecting the probability of mutation, can you just move? Yeah. Once we fixed upon the probability value of the mutation, then what we essentially do is compare the generated random number with the mutation probability. So if it is less than that particular probability, then you decide, okay, I will do the mutation. If it is greater than that, you just don't perform the mutation. The next step is identifying the particular location where you want to change the bit. How do you do it? Essentially, it's the same method as before. So we just randomly select the number from the entire length of chromosome. If your chromosomal length is L, you kind of select generate a random number between 1 to L and go to that particular site for mutation. So say we have got a number 5. So we have chosen the site, we have decided to perform a mutation. The next step is to actually do it. So this is the same string which we considered previously. So I have decided my random site as 5. So we'll just go to the 5th site. Mutation is essentially bit flipping. I mean, if you have 1, you convert it to 0. If you have 0, you just convert it to 1. That is about local mutation. But as you can see here in this, what we have essentially done is like you have taken only one particular bit and you kind of flipped it from 0 to 1 or 1 to 0. What would happen by this is like you are kind of only changing one variable at a time. Like this entire chromosome has so many parts to it. Like some part of it may be one variable, the other part might be some other variable, the third part might be third variable. So with this particular technique, you are kind of changing only one variable at a time. So this might be slower in convergence for some particular problems. So what we will be discussing next is something called a global mutation operator, where instead of just one, we'll go with multiple. We'll see how we'll do that. So previously we just changed one bit. Now what we do, say we have a length L. The next step is we'll generate sequence of random numbers. Like we'll continuously generate random numbers of say dimension L. So if your chromosomal length is 8, we generate 8 random numbers. So for this particular chromosome, say we have these numbers as generated. Now the next step is basically I need to choose some particular value for the mutation probability. Say I have chosen a value of 0.3. Our next step is essentially to compare the random number, the number which we generated with this particular probability. And then we come up with saying if the random number generated is less than mutation probability, then you do the bit flipping. Otherwise, you do not. This you do for all of them. Say for the first one, we consider 0.2 with 0.3. So since 0.2 is less than 0.3, you essentially decide that you need to perform mutation for this particular bit. The next you go to the next bit. You again do the same thing. You compare 0.35 with 0.3. You essentially say, yeah, I don't need to perform here. And then you come to 0.05. 0.05 is again less than 0.3. So essentially you have to perform here. You just repeat this for the entire sequence. You happen to find out that these three are the places where the random number generated is less than the mutation probability. So you have to flip these bits. So you just change ones to zeros and zeros to ones. So this is what you end up with. This is about mutation operator. The next operator which we discuss is the survivor operator. There are basically two schemes in this, either the mu plus lambda scheme or the mu lambda scheme. What essentially we are doing in this particular survivor is like, okay, we have taken an initial population. Then what we have done is evaluated the fitness for the entire population. Then we have passed them through a selection operator, which essentially kind of identifies some of the solutions from the population that are better to go into the mating pool. Once the good solutions reach the mating pool, or maybe the probable candidate solutions reach the mating pool, we then pass them over crossover and mutation operator. Those two operator kind of gives you new offsprings. The output of crossover and mutation is what we call the offspring. Once you get the offspring, what you essentially do is survival. Now you have a set of parent solutions and you have a offspring solutions. Now you want to pick the solutions that would go to the next generation for the loop to continue. So the first strategy is essentially you just take the complete set of both parent plus offsprings and select the best solutions of them. How do you select best solutions? You just sort them based on their fitness. Say if you want to minimize your objective function, you just take the fitness values, sort them in ascending order, select the top n solutions. Basically, n is your population size. If your population size is say 8, you select the top 8 solutions. This is one kind of strategy. The other approach could be like, why should I select from parent? I will only select from offspring. Then what you essentially have to do is repeat the variation step twice. Since you, like previously we have seen, like these steps are not deterministic steps. These are all stochastic, in the sense you are kind of generating random numbers and doing some, like you are kind of taking your decisions probabilistically. So when you repeat the same crossover and mutation on the same population the second time, you may not get the same solutions which you got previously. So what you essentially do here is like you repeat it twice or thrice to get as many number of offsprings that you want, and from these offsprings you select the best possible solutions. This is the second scheme, new lambda scheme. Which one to use? Again, it depends on your particular domain, and it actually depends more on your objective function and sensitivity as well. If you are having a particular function which is kind of more sensitive, then just choosing from the initial guess might, if your problem is very sensitive, the initial guess will kind of dictate your solution confine your solution to very small regions. So then just selecting the pair, if you need to have a input from both the parent as well as offsprings to carry to the next generation. If you are not using the same, if you are just using the offspring, you are just kind of confining yourself to whatever you have discovered, the news page and there is a name to it. We'll just see. It is called an elitist strategy. This has been discussed in the course. If you have gone through, what it essentially says is like, if you have found out some best individuals, you want them to go to the next generation. Say if there are some best individuals in the parent generation, if you just pass them to the next generation, more likely they are going to be the global solutions. The other strategy is like, I just don't want to be biased to anything. I will just go with whatever comes up in the offspring. That can also be done and might be slower in convergence. We usually prefer the first approach. Like that is the approach we'll be discussing in the course. Okay, now till now we discussed about binary encoded genetic algorithm. So the next week of lectures, the third week of lectures, starts with what is called some of the limitations for this particular type of approach we have been learned in the first 2 weeks.
Excuse me.
Yeah.
This how to select crossover probability PC and mutation probability, because if mutation probability if we keep high, then it is not a good practice.
Yes.
Similarly, crossover should be higher side,
yes.
0.7 and above.
Yes.
How to select this? Because this affects the result.
Yes. And like as you know, like these algorithms are stochastic and you do not have any mathematical proof saying that this algorithm will reach you to global optima. What you essentially do is it's something called like research, where you kind of see all possible you decide, okay, these are the parameters that I would be searching for. Say crossover probability should be too low, so you start with something like a very high value and then mutation to be a very low value. You see whether the solution converges or not. If not, then what you essentially do, change the crossover. Say you decrease the crossover a little bit, decrease the crossover a little bit, and do the same again. This is a kind of an iterative, like you kind of do it till you get the solution.
Yeah. Okay, sir.
Yeah, we'll come up to this limitations of some of these algorithms which we discussed previously. The first one is essentially the one which we discussed previously also when we discussed about precision. So what essentially is happening is you have a search space from say some particular value 0 to some 5 or something. This is the bounds for that particular variable. When you are kind of saying that I want to represent this entire space using a chromosomal length of L, what essentially is happening, you are kind of changing the space from 0 to 5 to 0 to 2 power L minus 1. So what is happening here is discretization. Your entire space is getting discretized. Now you can only find solutions at these particular points. You do not know what is happening in between. This is one of the limitations with the kind of technique we learned before. The next limitation is what is called the Hamming cliffs. So let's say we have two individuals. Let's consider these binary strings. The first one, if you convert, you get a value of 16 and 15 respectively. So if you see, 16 and 15 are kind of very close to each other in terms of the distance between both the points. They're very close to each other. But when you see that, like if you want to move from 15 to 16, what you essentially have to do is to add or subtract 1 from the previous number. But in the binary, with the previous whatever operators we have learned, you have to change lot of bits. Like if you want to go from this to this, you kind of have to switch all the bits. Like you have to change all the ones to zeros and zeros to ones. That is a lot of operations. So only when all these operations happen, only then your solution changes from 15 to 16. So it kind of takes you through a lot of steps to change. Say you need to have kind of 6 mutations to happen. Like each mutation probability is set to very low. Say if it is 10% or something, then probability of happening all of them will be like, you need to kind of say with a probability of 10%, it's like every 10 generations you kind of have one mutation. So only after like 10 power 6 generations or something, you will come up with a solution where you kind of move from 15 to 16. So this is kind of one of the limitation with the binary coded. So what do we do with this? The limitation is essentially coming because of the way you represent it. So the idea is to change the type of encoding. We just use real numbers. Why do we have to use the binary strings? We can just use the real numbers and do away with it. The first question is like, okay, we have developed some of the techniques before. Now, if I have to change this particular encoding scheme from binary to a real number, which of the following steps will be changed in that? So we'll just take the previous algorithm which we discussed. Which of these steps do you think will be changed if I change the encoding scheme? Any volunteers? I hope I got my question clear.
Excuse me.
Yeah.
How to decide the population size?
There are some heuristics in the sense it's like a thumb rule kind of stuff. So it depends usually on your number of variables. So if you say you have one variable of say dimension 8, I mean you have 8 independent variables x1, x2, x3, so on up to 8, then you choose a population which is twice the number of twice or thrice of that. Like these are all kind of heuristics. There is no hard and fast rule that or there is no mathematical proof saying like if this is your variable dimension, this is the population size you have to take. These are just some kind of from experience you say. Most functions it usually works that way.
So for 10 variables, this population of 50 will be good enough?
Yeah, it depends on the diversity as well. Say like previous case when we considered, if you have a variable dimension of 10, you can start with 50, but then you can see like you can kind of do it in a reverse way. Like you take a population size of 50 and see how it evolves over the generation. If your convergence rate is much kind of slow, or it's kind of say if you have something like generation versus your function value, if this is kind of very slow, which means you are kind of converging much fast, which means there is not enough generation in your original population, then it's a kind of a hint to you that you need to increase your population size. You just can't decide ahead of time. Like you just see how it evolves, and based on that you kind of come up with your, okay, this is wrong, so I need to change it.
Does it depends upon how many variables are very sensitive to the design?
Yeah. It depends on your objective function, the way you, and actually it more depends on your constraints. Constraints will be the ones which will kind of direct you. Okay, we will see when it comes to multi-objective functions, that is even more complex. That we'll be discussing anyway.
Okay.
Yeah, for this particular case, okay, let's just stick to the problem of this original case. So if the problem which we identified, the two limitations which we identified are basically the Hamming clips, which essentially says if you want the way to go from 14 to 15 is much different from 15 to 16 in a binary string. And then the other problem is basically we are kind of discretizing the search space. So what we are deciding now is like, okay, I don't use binary string, I don't use binary encoding, I go with real encoding. So if I were to change the way I represent the solution, which of the following steps do you think will be changed? As you can see, the first step will right away change because instead of binary strings, now I am using real numbers. Initializing random population, evaluating the fitness functions, all this won't depend upon the way you represent the information. Essentially, they are going to be remaining the same. The selection operator, as we discussed before, selection operator essentially depends upon only the fitness functions. So even that is not going to be changing. But when it comes to crossover and mutation, previously we have learned like we took the string in the binary format and then we have performed this operation. So if I am going to change the way I represent the actual information, then both the crossover and mutation operation have to be changed. Final operator, survivor operator essentially depends only on the fitness function, so that is also not going to change. So these are the two steps that are going to be changed if I change the way I encode information. So now we discuss about some of the techniques, some of the algorithms in real coded. The first one is the real coded genetic algorithm. This is the one kind of one which we are discussing till now. There are other strategies like evolutionary strategies, differential evolution, particle swarm optimization, and artificial bee colony, which will be discussed anyway in the coming up weeks. Now to understand real encoding, we'll just go through some of the one example. Say suppose you have some function f of x equal to x square and your objective is to minimize this function. Just with this particular case, it's like we know from prior experience that f of x equal to x square is minimum when x equal to 0. This is just for the case of, for the sake of explanation, we are just taking this example so that things will be clear. How do you operate various operators? The next is we have some various bounds for these variables. It's like we are saying x between 1 and 5. So for this particular domain, now because of your constraints, your minimum has changed. Previously, when there are no constraints, you have a minimum of x equal to 0. But now when you have a constraint saying x only belongs in the region 1 to 5, you have a minimum at x equal to 1. So we'll just take the previous technique. So the first step is to kind of represent the solution. Now we are essentially doing real encoding, which means we just don't do an encoding. We just use the real numbers as it is. So we don't have to do anything in the first step. The next step is initializing the population. So for this, basically what you need to do is to first select your population size, which we discussed previously. It's like it depends upon your case. So for our case, we are just considering a population size of 4. And this number is up to you. Like you can actually choose 8, and you can experiment with all of them. But usually we start with, for this sake of example, we are doing only hand calculation. So we are considering a number 4 for sake of simplicity. So what essentially is we have some domain, we have some bounds, say x varies between 1 and 5. So what we do next is essentially randomly generate 4 points in this domain. So we are starting with a uniform distribution. So we consider a uniform distribution and then generate 4 random numbers between 1 and 5. So these are the numbers I am generating. The first number is 1.6. Second, I got something like 4.2. Then I got something like 2.2. And then I got a fourth number of 3.4. Say these are the 4 points I have picked. And this is what my population is. So now my population has 4 individuals, each one having these particular values. Now let's go to the algorithm. Okay, what is the next step? Next step is essentially evaluating the fitness of these individuals. We have the objective function with us. So what we do, the objective function is f of x equal to x square. Once you have all the objective function, all the values of x, you just perform x square for all of these individuals. Like you get these fitness values. Now we have this. The next step is selection. The next step is survival of the fittest. That is basically selection operator. As we discussed previously, like selection operator essentially depends only on your fitness values. You doesn't have to account for what is the actual value of the decision variable. It's basically only the fitness values that are important for the selection operator. So we just forget the values of x, then we will be dealing only with the f of x. So these are my fitness values. We are sticking to binary tournament selection. So it's the same operation, same operator we discussed previously. We start with selecting two individuals. Say I am selecting these two individuals, A and B. My next step is to compare both these fitness values. Here my objective is to minimize. So you can see here A has a value of 2.56, while B has a value of 11.56. So if I apply the tournament selection, the one with the minimum comes out. That is essentially your A, 2.56. Similarly, you kind of repeat it again and again till you get the size of the mating pool to be equal to the population size. Essentially here population size is 4. So you kind of repeat this step 4 times to generate your entire mating pool. So say suppose these are the fitness values I get after that. Say I get 2.56 twice, 4.84 and 11.56. What essentially happened here is, like, you can see, like, if these are my final individuals, this particular individual has not appeared in the mating pool. As you can see, this particular selection operator has kind of did a good job in kind of eliminating the bad solutions and kind of preserving the good one. So the good one is 2.56 has been preserved twice. So if we just see the values of variables, it's like 2.56 we have twice, and then we have 4.84, and 17.64 is kind of disappeared now. Okay, now comes the next step. The next step is your variation step, the crossover and mutation. We discussed previously, like, if you are going to use a different type of encoding scheme, then these operators have to be changed a little bit, because the way we decided previously needs the variable to be encoded in a particular format. So how do we go about it? Now we'll start with the crossover operator. First step is, like, how do we design a crossover operator? Now we know about a binary crossover operator. Now we want to implement a real encoded crossover operator. So we'll just have a look at binary crossover operator, just see what are some of its properties, and then we'll kind of come up with our own operator for a real encoded variable that kind of simulates the behavior of the binary encoded one, which essentially means there are certain properties of this particular operator in binary as well as real encoding that has to be preserved. So we'll have a review of what are the properties of that particular binary encoding. The first one is, if you consider two binary strings, if before and after crossover, the average decoded value of both the strings will remain same. We'll just see whether it is happening or not. If you have two variables like this and you are randomly choosing some site for crossover, when you kind of exchange the tails, what is essentially shares is the mean value of the strings before exchanging and after exchanging remains the same. If you look at this, we'll just expand this to see a bit clearly why that happens. Is the first one, when you expand, kind of convert it into decimal, this is what you get. The second string is what you get here. What you're essentially trying to do is swap this here and move this here, and then you kind of are doing summation of this and this. By this particular operation, the total summation is not going to change just by flipping some numbers here and there. It's like you have A plus B plus C plus D. What you are now doing is changing B and D from their positions. So what you have now is A plus D plus C plus B. So the final value is not going to change. This is what we meant previously. So this is some kind of property for the crossover operator we have chosen before in binary encoding. So whatever operator I am going to design in real encoding should also have the same property. The next thing is called the spread of the operator. That is basically defined in this particular way. We use the variable beta. Beta is equals the modulus of O2 minus O1 by P2 minus P1, where these are my offspring solutions. And these are my parent solutions. What does this say exactly? Well, if your beta is something like this, as you can see, the beta value ranges from 0 to infinite. It can be any value between 0 and infinite. So we have essentially three cases. There is some special case of one. So the first region, when beta belongs to 0 to 1, is something called contracting. 1 to infinity is what we call an expanding, and the exact value when beta equal to 1 is what we call stationary. So what we are trying to do is kind of simulating the behavior of the binary crossover operator which we defined previously, simulate it in a way that it functions for a real encoded variable. That is what we call simulated binary crossover operator. This is the formula for calculating that. This is my beta over here. As you can see, when you have these two variables, you can kind of rearrange this a little bit. This particular value of beta is given by this particular relation, where ui is the uniform random variable 0 to 1. And as you can see, eta is a parameter. Eta is the user defined parameter. This again we have to kind of decide how much to keep. This will decide the value of beta, which will go into this particular equation. To get an understanding of what we are essentially doing, we will see, like previously when we are doing a crossover operator, you are kind of doing say single point crossover. You identify a random site, exchange, and then you come up with new offsprings. Say you have originally some domain with P1 and P2. We generate offsprings. Offsprings can be anywhere. The one, say the O1 can be anywhere, somewhere here, or somewhere here in the entire range. But wherever the offsprings are, the two offsprings should be located in such a way that the center remains unchanged. So this is my center for P1 and P2. Say center. The one offspring, say O1 is here. Then what this essentially means, like O2 should be located in such a way that the center remains unchanged. So your O2 will be outside somewhere over here, so that the center remains unchanged for the population. So this is the kind of binary operator we decided. Now we are coming up with the same strategy to come up with another operator in real encoding. So if you are using P2, P1 all as real variables, if you can see here O1 and O2, you essentially, if you sum up these both equations, you are kind of getting O1 plus O2 equal to P1 plus P2. So the centers are remaining unchanged. So this particular operator preserves that property. We will see how exactly, like what exactly is this. You can kind of slightly rearrange these equations. This is what we use for. You can see what we are just doing is rearranging the equation a little bit. We come up with this equation. This is fairly easy to remember. Now we will see what exactly happens when we can do O1 plus O2. Is essentially these two cancel out, so we get P1 and this is my P2. So this is what is preserved. But what exactly are we doing in a crossover operator? Let us understand that a little bit. So say I have one population P1, I have another individual P2 in my original domain. The first step is basically you select the midpoint, say some that is somewhere in between P1 and P2, like half of P1 plus P2. Once the midpoint is selected, you know the distance between the midpoint and this particular P1 is essentially half of P2 minus P1. Is the same distance on the other side as well. The midpoint and P2 is also essentially the same. What we are trying to do now is you want to pick one of these sites randomly, like it is from the midpoint you are kind of trying to scale this particular distance and get to a new point. So you can either do it to the left or to the right. What do? You flip a coin. If you get a head, you go to the left. If you get a tail, you go to the right. Or in a programmatic, if you want to do it in programmatically, what you essentially do is to generate a uniform random variable from 0 to 1. If you get a number less than 0.5, you kind of choose left. If you get a number greater than 0.5, you choose the right. That is, both are equivalent of saying that 50% probability choose one and the other with another 50% probability. Say for suppose I got to choose left. So this is my actual value. Now what I do is to scale this particular value. The first step is choosing the particular scale. What value of beta should I use? This is the same formula which we discussed previously for beta. Here, as you can see, like ui is a uniform random variable from that will be between 0 and 1. Eta is your parameter that user has to define. What exactly, like what is the effect of eta on the value of like how does eta affect your crossover? We can just have, if you can see these expressions, what it is like. If you have two individuals P1 and P2, what we are essentially doing is, if you just see it from a perspective of probability, it's like you have some probability of choosing these numbers close to this one. The steepness of this particular portion is what is indicated by this particular eta. So if you are kind of increasing the value of eta, you are kind of increasing the steepness of this. So if you kind of have a higher value of eta, you will kind of probably end up with something like much steeper slope, which means the probability of getting individuals closer to the parent solution is higher. Once you choose a particular value for beta, you have to apply that scaling to this particular vector shown below. So say I've chosen some particular value of beta, then what we essentially do is take this particular value and multiply it with beta, then I get a scaling. So that might be actually lesser, or this particular figure shows about a lesser value, you can actually have a much larger value. Like if beta is greater than 1, you kind of end up with a much larger value, and this ending point is where you will be getting your solution. So if beta is less than 1, this is where you get a solution. If beta is greater than 1, you get somewhere over here. The similar, you do it on the other side. That will be your next solution. Now we have done about crossover. Now we'll discuss about, okay, this is what we got left with after tournament selection. Like these are the 4 individuals we got once we do the tournament solution. Now as we have to do the crossover operator, what we do, take these original values. The ones are fitnesses, but now we consider the values of x. Values of x are what are important for crossover. For crossover and mutation operator, we don't need the values of fitness. For selection, we don't need the values of the variables as such. We need only the fitness values. What we do here, we just pick 2 solutions. Say I've considered those 2 blue dots. I'm considering both of them. What I'm doing is the same step. So we'll go one by one. So it's like we'll take the first one and then the second one. Now I've picked 1.6 and 2.2. We know the next step is basically to select the midpoint. The midpoint is something like 1.9. Now we know like 1.9, the difference between the midpoint and the left half is say 0.3, and the right half is also 0.3. The next step is to choose the value. I have to choose one side randomly, or you can actually choose the left one. We'll just say left one. So I've picked this one. The next step is basically to choose the scaling. Scaling is essentially choosing the value of beta. So this is our previous formula for beta. So for this particular, to choose the value of beta, the first thing I need to come up with is to decide a value upon eta and a value for, I need to generate a random number and get a value for u. So say I have got a value of u equal to 0.08 and eta equal to 2. For this particular case, we get beta of 0.8. You just substitute, say we've taken u equal to 0.08 and eta equal to 2. So u equal to 0.08, so that is less than or equal to 0.5. So we are going to use this particular formula to calculate beta. Once you do that, you get a value of 0.8. So what that essentially means is, now you have something, this particular value, now you want to scale it by 0.8.
Excuse me?
Yes.
How did you decide this eta?
This eta is kind of, see, when you have, if this is my domain, eta will tell you what is the, eta is kind of, if you increase the value of eta, you are kind of increasing your probability that are closer to the parent solution. So if you are in your initial stage of search, in the sense like, when you are initially starting with your optimize, like when t equal to 1, the first generation, second generation, something like that, what you essentially want to do is to explore the search space more. So you want solutions to be kind of far from the parent. So you kind of choose a very lower value of eta. But as you go to more generations, what you essentially end up is like, you will be closer to some of the local optima. Then you know better, like, okay, it's better to choose more individuals from near to the parent than close farther from them. So what you do is choose a value of higher value of eta. Like, depending on how your solution is converging, you choose this value of etas.
You have taken eta equal to 2.
That is just for an example. We can take eta equal to 2. You can actually take 4, 5. What happens is, if you have chosen a higher value of eta, then this particular scaling, whatever you are choosing, like the solution will be closer. If you have chosen say eta equal to 15 or something, what happens is the offspring might come somewhere here. If you have chosen a smaller value of eta, then your offspring might come somewhere here, or it will be far from here. So like you get somewhere here, somewhere here. If you choose a very high value of eta, you'll get very close to this one, which I would like to avoid. So I'm just taking a lower one. I just want to explore the search space more. Okay. Now for that particular case, we got a beta of 0.8. So what we do is to scale this vector. Like I got 0.3, and then you just scale it by the beta. So you get 0.24. What you essentially do next is basically move this point, the midpoint, like you choose an offspring equidistant from this. So that is this point. So like as we discussed previously, the basic property of this particular offspring is that you maintain the symmetry. I mean, the center point has to be the same. So if one offspring is this particular point, the second offspring should be somewhere here. That is also kind of at a distance 0.24 from 1.9. So this is how I pick my solutions. So the new solution is 1.66. The other one will be 1.9 plus 2.24. That's 2.14. So one solution is 1.66. The other one is 2.14. Now this, I just got one offspring. You have to repeat it kind of again till you get your population size. Say here our population size is 4, so you kind of repeat it 4 times to get 4 solutions. So this is my original population. Now if I do the same steps again and again, what is happening is like, say first time I got 1.66 or 1.7, and just if I do it again, I got something like 1.1. If I do it again, I got something like 1.8. If I repeat it again, I got something like 2.9. As you can see here, it's like after doing crossover, I got different kind of solutions. The ones with these ones are basically your original parent solutions, and these are your offsprings. Once we are done with crossover, the next step is your mutation operator. So here we pass individual, not like for crossover operator, you essentially need 2 inputs. With 2 inputs, you come up with 2 outputs. In mutation, you take 1 input and 1 output. For real encoding, what we are doing is polynomial mutation operator. We just do the following. We have a range from upper limit to lower limit. You kind of scale the range and kind of we'll just see pictorially what does that mean. So if this is your domain from lower limit to the upper limit, and your actual input, like basically the offspring solution which we calculated before, is somewhere in between. Say x is somewhere in between this. What you want in mutation is basically you want to have a newer solution y. Now how do I know where to keep the y? We use something called delta. This delta is a scaling parameter that we are going to use. How we calculate it is the same. We do it in the same kind of way we have done it before. We have some parameter called eta, which is a user defined parameter. So depending on eta is low or high, you kind of will get values closer or farther from the original solution. So if you are choosing a very high value of eta, then you are more likely to get more oscillations. If you get too lower value of eta, then you are more likely to take more steps to reach your convergence. So you need to kind of, it's a kind of a trade-off that you need to balance. Only some particular value of eta will give you a compromise between the time required to converge versus the required diversity in the population. So once you define the eta, you get the value of, from this, using this particular formula, you get a value of delta. Once you got the value of delta, you just substitute it back into your original equation. So what we are saying, so this is my delta times xu minus xl. So now here again, we are saying like it is x plus something. So delta can actually be positive or negative. Or if you always get delta as positive, if you like this function is basically one of the suggestions given by one author, but you can actually choose something else. Like you can actually define your own variable. So in such a way that delta can be positive or negative. What you do essentially to introduce more stochasticity, you can kind of again put a random number here. Say you flip the coin. If you get a heads, you kind of go to left. In the sense you say it will be x minus instead of plus. Or if you get a tails, you kind of say I'll do x plus. So this is the range I am going to skip the value of x. So I translate it, I got a new point. So this is my output of the mutation operator. We have discussed about one possible crossover and one possible mutation operator, but there are other combinations possible as well. We will go through quickly each one of them. The first operator is a linear crossover operator. Say you have two parent individuals, P1 and P2. So the idea behind this is you have certain limits, XL and XU. These are your variable bounds, and you have two parent solutions. Using this linear crossover operator, you want to get offsprings. What you do is first select the midpoint. It's the same strategy before, you select midpoint, but now what we do here is instead of just selecting a midpoint, we do it on either side. So this will be kind of equal distances from both P1 and P2. Now we do it on the other sides as well. We go a little here and we go a little here. So I generate a second point to the left of this, that is what O2, and I generate another point to the right of it, O3. So what we are essentially doing is previously my search space is essentially P1 to P2. Now what I have done by introducing these operators, I've kind of explored my search space from O1 to O3. So I'm kind of expanding my search space. What I do next is basically now I have three possible offsprings like O1, O2 and O3. I'll select the best two out of them. These best, the idea behind this is simple, like if you have two input parents, you just want two offsprings. That is how the algorithm has been structured in the original way. So I just want two outputs. So out of the three generated values, I choose the best possible two. Best in the sense the ones having, if you are a minimization problem, you just select the minimum of the three. If it's a maximization, you select the maximum of the three. As you can see in the previous operator, it is just a linear case. It's like your problem will kind of expand in a linear way. It just wouldn't know how to expand based on the dynamics of the problem. Now we come up with some other operators called the blend crossover operator. This is also similar. We consider the same domain P1, P2 between some limits XL and XU. What we do here, previously we have taken the midpoint, like one point in between P1 and P2, one to the left, one to the right. But the distances there are fixed. Fixed in the sense like you kind of fix the distance to a scale of 0.5 times P1 minus P2. But you have to do it that way. The idea here is, okay, we will change it dynamically. So here we define some parameter called delta. This delta essentially decides how much to the left of P1 you need to search and how much to the right of P2 you need to search. And this delta is again a stochastic. We just don't want to bias ourselves. We want this to happen randomly. Then once we fix delta, we go to the left, to the right, both with the same delta. So we are going symmetrically. Then we get the entire range from P1 minus delta to P1 plus delta. This delta, how do we calculate, is to something called alpha times P2 minus P1, where for the same reason you can have a name called BLX alpha. Like this method is also called by this particular name. This alpha is a parameter which introduces the randomness into our selection in our crossover operator, and that is a user parameter. Like you can kind of change it as you iterate through your generations. Say like during initial parts of time, you might want to constrain to some areas. As you get refined more and more, or maybe if you are reaching some kind of, if you know that you are kind of converging to one of the local optimas, then you can increase the value of alpha to increase your search space. You can control it through iterations. Actually performing this operation is like once you got the value of delta, okay, this is my region P1 minus delta to P1 plus delta. So from this region P1 minus delta to P2 plus delta, you randomly select one point, or if you want two outputs, you just select 2 points from this randomly. And the next kind of possible variant is the simulated binary crossover, which we discussed previously. So it's the same steps, we go ahead. But here, as mentioned before, you have some kind of probability for selecting the variable. It's like previously we have kind of constrained ourselves to within delta, or in the case of a linear crossover operator, we told we'll go only 0.5 times P2 minus P1. In the second case we told, okay, why only restrict to 0.5? We go with some other scaling parameter called alpha. But now what we are saying, why do I have to limit myself to alpha? I can get any value between P1 to whatever is my limit of that particular variable. So now here we generate a number randomly between all these, but all these values are not equally likely. In a sense, like values much closer to the bounds may not be my optimal solutions. It may or may not be my optimal solutions. But what I'm trying to do is, okay, when I'm searching, I'll do search in a way where initially I'll try to focus in the region where my parent solutions are there and explain in a very limited area. So it's like you want more populations to come up very closer to P1. Similarly, for P2, you want more solutions to come closer to P2. So with this probability distribution, you generate the random number. Like one possible approach is you can use a Gaussian distribution with the mean value of P1. So say for example, the P1 value is say 2. The sigma range will be some, as we know, like for a Gaussian distribution, the value falls below around 3 sigma or something. So you can kind of say 3 sigma is P1 minus XL. From this you get the value of sigma. So we generate a random number from the Gaussian distribution, and then you get some value over here, something like this. What you will frequently encounter is most of these distributions are not bounded. In the sense, the output of these distributions will be somewhere between minus infinity and infinity. But actual bounds of the variable are between XL and XU. So what you do is one approach is to just truncate them. In the sense, say you got some value, say your XL is 2, but you got some value like 1 or something. What you essentially do is when you get 1, you kind of change it to 2. Like you actually truncate it. The other ways are you kind of change the distribution in a way that you get the values below XL or above XU are not at all possible. In the sense, the probability of getting those values are 0. You can kind of formulate distributions in such a way. Or you can kind of directly put a hard rule saying if it exceeds, just make it equal to that bound. We discussed how to perform the simulated binary crossover, the formulas for getting the beta values and all that previously. So now we'll stick to another one called the fuzzy recombination. It is similar to the previous one. It's the binary simulated one. The only difference is like this. In this particular scenario, we are not varying eta. The eta which we discussed previously, we are kind of fixing it to 1. So what we are essentially saying, we don't have, like we know there is a problem. So what we do, instead of the Gaussian kind of one we discussed previously, here we consider a linear kind of one. So we say, okay, with this particular thing, you can see here like this particular width, what you see here is a parameter which we have to define again, or which something which is adaptive in nature, in the sense which changes as iterations progress. So when you choose this particular kind of distribution, you are kind of limiting yourself to within the domain. Only towards the boundaries, you can again put another hard rule to kind of say, okay, if you exceed this, you need to restrict yourself to the bounds. Here, this is the case equivalent to the one which we discussed. PLXR, sorry. This is equivalent to the binary crossover where eta equal to 1. The next one is unimodal normally distributed crossover, like the one which we previously discussed. This one is slightly different in the other ones in the sense, like till now what we have encountered is you have 2 parents and you get 2 offsprings from them. But this is slightly different in the sense it takes 3 parents into consideration and gives 2 offsprings. How do we do this? We'll just go through this a little slow. First thing is to consider 2 individuals in your search space. Say this is my search space, like considering one diamond. I have 2 individuals, say P1 and P2. The basic property in the sense like the center point should remain unchanged, should be conserved always. So we'll start by considering the midpoint, say PC. Now what we do till now, whatever algorithms we have used, it's more or less surrounding around PC. Like you choose a probability distribution around P1 or around P2 or around PC, or you say okay, this is the spread I want. But what we do here is like, okay, why to use only 2 parents? We will try to get more information. In order to do the crossover, we will get information from another parent as well. So we choose a third individual in the solution, not along this particular line. So when you have this third individual, you can kind of calculate this perpendicular distance, d. Now using this particular distance, you know the distance between P2 and P1, which is say suppose small d. Now we use this particular formula to calculate the offspring. What you're essentially doing is like you take the midpoint and you kind of scale both the distances. Now you are getting, as you see here, it's like eta d plus small eta times p, you get some vector over here. So when you are using a linear combination of capital D and small d, which are orthogonal vectors, you get some population here. So the previous algorithms will always give you some solutions only along this particular line. So if you have something like this, if you use one of the previous algorithms, what would happen is you can consider one of the possible cases. So if you consider a triangle over here, what will always happen is if you consider P1 and P2, you will get some offspring over here. If you consider P1 and P3, you get something over here. If you get P3 and P2, you get something over here. You will always get along the edges of the triangle. You will never go inside this particular region. So if you use this particular algorithm of this normally distributed one, here what happens when you choose something like small d and capital D and you are using a linear combination of both of them, you will somewhere and end up here. So instead of the triangle which, sorry, one second, you might actually end up somewhere in between. So you are kind of exploring even further. So this is another kind of crossover. The main idea behind crossover is to kind of explore your search space in a much better way.
Excuse me?
Yes.
Why it is called unimodal?
It's essentially because you have just okay, one second. No, I'll get back to you on that. Yeah, I'll get back to you on that.
Okay.
Just give me a second, I'll just note it down. Yeah. Now we are done with crossover. We'll have a brief review of what the mutation operators are. There are several possible options. The first one we start with is a random mutation. So this is saying you have certain limit between XL and XU. What you do is you have this, like in a mutation, it's like you give one input, you get one output. So X is your input, that is within the bounds of that particular variable XL and XU. Now you want to randomly generate a new value. What you do? You select one region. Like it's same like the previous one we discussed. We have something called a delta, which kind of tells you how much variance you have to give for this particular, like it is like you have certain variable, how much variance you want, how much you want to change that particular value. Then what you do, you essentially have a region x minus delta to x plus delta. You choose from that region. You choose randomly from that region. So as you can see here, this is completely random. It doesn't depend on fitness. It doesn't depend on what the actual value of the particular, like whether the solution is good or bad or anything like that. It all tells is like you have some certain solution. You just select some neighborhood region for that particular solution, generate some get the next solution out of it. But as you can see in the previous one, what we have considered is like all the possible solutions between x minus delta to x plus delta are equally likely. In a sense, when you are near x, some particular value of x, getting a value of 1 closer to x minus delta or getting a value closer to say x plus delta by 2 or something are equally likely, which means it is not, usually it is not the case. Say consider the general evolution pattern for the sake. If you are kind of considering one animal going from one generation to the next generation, it is a very gradual process. In a sense, the next generation is more likely very closer to the previous generation. And if you go generation by generation, say after 5 generations, the one at the 5th generation is usually not closer to the first generation. So it's like, even if you consider a general engineering case for that sake, the probability of going from one particular solution to the nearest one is more likely than going to a much farther one, which is not captured in this particular kind. Here, all are considered to be equally probable. How do we solve this? Is by using a non-uniform mutation. So we say now here, okay, instead of considering equal probabilities, we kind of consider some other distribution which kind of give you this non-uniformity. In essence, the ones closer to x are more likely to find than the farther ones. We will come across several distributions to kind of do this. The main idea is basically whatever is closer to x should be having higher probability than whatever is far from it. There are a lot of distributions which exhibit this property. One is the Gaussian distribution. that will be our another operator. And actually what you can choose here is what the videos the professor has suggested using this particular scale. What you can see here is what you do, x plus delta is basically the same. You kind of translate from x by a certain amount called delta, but how do you choose delta is using this particular formula. Here the importance is in the value of r and a. As you can see, that particular a has something called small t and capital T. The small t is your generation number and capital T is the maximum number of generations that are allowed to be run. So depending on the ratio, like depending on where your generation is, you kind of select the value of delta. So if you are very far off into the generations, in the sense when you are close to when t is very like almost equal to approximately equal to capital T, this essentially becomes 0. So this doesn't have any weightage. So then you are kind of your delta is kind of constant. When you are doing your initial values of t, then you're kind of exploring more. Then it's like far off solutions are very less probable than the near ones. This is kind of what you call an adaptive one, which kind of changes with generations. And this b over here is some parameter. It decides how much weightage you have to give. If your b is essentially 0, then you are not capturing any effect. You can actually, as you increase more values of b, you are kind of making it more sensitive to number of generations. The other distribution you can consider is just the normal distribution. The delta, the previous one is just a kind of adaptive one. The other one is just simply use a normal distribution with some variance. That variance sigma is a user-defined parameter that user has to give. So these are some of the algorithms that are discussed in week 3. Any other questions that need some specific attention? We discussed about something. You have any specific questions that you need me to discuss, or we'll just go with one other example?
Hello.
Yeah.
There are so many parameters, alpha,
Yes.
theta, eta, so many things. So it becomes very difficult to how to handle these operators.
In the sense, like saying, how do we go about selecting some of these variables?
Selecting
or
the
something?
values, yes.
Yes. Yeah. That is kind of what you say. It's more of an art, in the sense only with experience you'll know, okay, how will I select this? You can actually see it in one way. The one way could be like you fix some values. What your only output is how your fitness function changes over generations. If your fitness is kind of remaining constant, either you have reached your solution or you do not have enough diversity in your population. If you do not have enough diversity, what are the things you can change? Basically what you are saying, if you do not have enough diversity in the population, that essentially means you need to increase your mutation probability. You need to increase your space for that search, like basically the delta which we were discussing previously. Only if you increase that, then you will kind of explore your search space. Or if you happen to see that your solution converges much fastly, like in a much faster way, like let me just share my screen. You asked about some other question as well. Unimodal.
Yeah.
Yeah, let me just go over that. Okay, that is essentially because your okay, the random numbers which you are considering over there. Let me just share my screen. Yeah, if you happen to see here, what we are doing is something like you can see this capital D and small d. You can think of this like an ellipse, right?
Yes.
These are my two epicenters kind of stuff, and this is like one of the parameters, and this is another parameter. So with this you can kind of come up with one ellipse.
Yeah.
So what you're essentially trying to do is within the ellipse you need to get one point.
Okay.
And unimodal is basically saying this particular probability density will be much higher only at the center. So it's like it has only one peak. So if you just draw this at a sectional view, this is your PC, you are more likely, like you will get something like this with much higher probability at the center. Okay. You can actually have, say you can also have other combinations. Let me just give you an example. If you can also have design probability distributions with multimodal, in the sense you have two peaks.
Yeah.
With two different values. This is what happens, say, which kind of example? We can think of, say, height of some students in a given class.
Yeah.
It will be more of a multimodal in the sense, usually the average height of male statistically is much higher than average height of a girl. And among the girls, the heights are again normally distributed. Among the boys, the heights are again normally distributed. So if you are going to pick some number from this, you are more likely to get two possible values. You can either get a height from the maximum height from the male or from the female, the average height from the male or female. So that is one kind of approach, but that is usually not the case. In this particular case, what happens is like you essentially get more values closer to this particular value. So you call this some unimodal one.
Is it to do with anything about at maxima occurring at different points?
No, this is a maxima in the sense for the probability distribution we have chosen. It has nothing to do with the objective function we have.
Okay.
This is only for the particular, like the probability of choosing some particular value. For the crossover operator, we don't have anything to do with fitness. I don't even know the fitness value, and where the crossover operator doesn't know what is fitness. It just takes the input values, does the operation, and gives us output.
You talked about this generation, capital T.
Yes.
Number of total generation. How to decide this one?
Yeah.
At the beginning itself, how to choose it? Because it depends upon these so many parameters, because they will affect convergence.
Yes.
So it may happen that if I decide a generation of 100, okay, it may not converge.
Yeah, you will then know that after 100 solutions, you're like, if you see your plot of number of generations versus your function value, and if you see something like this, which means like you have kind of you are saying you put a value of 100 or something, 100 number of generations.
Yes.
And this is your objective function. You can clearly see that it has not converged.
It is not converged.
Then what you do? You just take the population present at this particular generation and run the simulation again.
Okay.
And observe it. Like that's how it goes. Like these are kind of things that you can tweak in your algorithm. The only parameters like you have chosen before, like what should be my crossover probability, what should be my mutation probability, what should be the value of eta, what should be the value of delta, how should I change it over iterations, what should be the weightage should I give. All these parameters are like depends on, like you need to kind of tweak it in the sense you start with some values, then you see how each of them affects your particular objective function. For that particular objective function, how does it affect, and then you decide, okay, I'm increasing this.
Another thing, this binary coded and real coded
Yes.
this thing, which one is better?
Implementation wise,
Yeah, implementation wise means result wise also. Which can give better result?
No, as you have seen, what we are trying to do when we are defining all these operators is essentially to preserve what the binary encoding has done. See, when we decide that we design the entire performance of algorithm depends upon your selection operator. Like selection operator will be same anyway. It depends only on the crossover and mutation. That is where the difference are there between binary and real encoded. What we are doing over here is we are simulating what the binary encoder does actually. It's like in binary encoding, we have some crossover operator. Whatever it is doing, we are doing the same thing. We are kind of maintaining that the same properties are there for whatever crossover operators we are defining here. With all these operators, the mean is preserved. That is what the same happens with binary as well. So it's not going to be changing much. The only difference is like the way your coding might get simpler in real. Here you are kind of have some analytical solutions you can do, but in the previous binary you have to store all the strings. You are dealing with strings over there. Your crossover, mutation operator, all of them operate on the strings.
Yes.
You have to store all of them. That might be a different task. Here you don't have to do all of that. Here again you have a limitation in the sense of say previously we know what precision is there. We have discussed about the limitation of a binary encoded algorithm is basically the precision. The precision is kind of fixed by the encoding length. Even in real encoding, you have kind of have a precision limitation when you implement it on a computer. That is essentially your floating bit precision you are having. If you are using some 64-bit computer, there is certain. It can only represent a 64-bit number. It won't be able to do. It won't be able to store much decimals, more decimals than that. That will be your limitation. So you are kind of.
But in binary coded, you have liberty to choose certain variable of longer means string length, longer bit.
You have some flexibility over there.
Yes, flexibility is there.
Yes.
Suppose in one particular design, if a variable is affecting too much, that I can increase the length, bit length. But in real coded, this facility is not there.
Yeah, there are some trade-offs. But essentially what happens in real encoded, as you can see, like what you can do over there is in that crossover and mutation, the delta which we are saying, like eta or delta, whatever we are saying, if you do not require that much precision, you can kind of increase the value of eta a little bit. So
eta value.
Yeah, eta value in the sense. So if your variable is much sensitive, choosing a probability density like this is versus this.
You have taken eta equal to 2, I think, no?
I have taken eta equal to 2, this particular case.
So how much we can take it?
No, you can kind of increase it to any level, like 10, 15 is also fine.
Okay.
So what that essentially determines is this particular value. So if you see in this particular case, you are saying like you have some variables which are more sensitive, right?
Yes. So if I increase the eta, this distribution becomes steep?
Yes.
Okay.
Then you will be more likely to be very close to the previous one. So you will get that more precision. Unless if you consider this particular case, you will kind of decrease your precision. That is in the crossover. You can do the similar in mutation operator as well. Like in the mutation which we discussed, you can kind of increase. Like if you are using just the random mutation, okay, leave this random mutation. Here you won't be. In this non-uniform mutation, you have that flexibility. You can kind of change the steepness.
Yes.
But in the original solution representation, you don't have anything to do. Only here you can tweak those things.
It means if I need more accuracy, then I can go for a steep variation. If it is
no, not necessarily. If you want more accuracy in the point here by increasing the steepness is we are saying when you are doing mutation or crossover, you just don't jump off too much, because if you jump off too much, you might miss some solution in between.
Okay.
So these are all random in the sense, like random in the sense you cannot guarantee that you'll get something by this. You can only say the likelihood of getting this is much higher than the previous case. If you make it steeper, you can more probably get accurate solutions. If you make it kind of a flatter, then you might skip that. I mean, the actual precision you want might not be there.
This crossover, this ensures a larger domain.
Sorry, I didn't get the question. Larger domain in the sense?
Search area.
That is to enhance your search area.
Search area. Yes. And mutation, what it does?
It's to kind of, if you're stuck in some local optima, this mutation will kind of get it out of you. Like mutation doesn't depend upon your current, like when you do crossover, you're taking two parents and doing that, right? So if you have some given parent population, you're kind of confining it to them. Say you can consider this like you have some all humans, and if humans, like if the crossover is happening only across humans, you get only humans.
Yeah.
That are not that intelligent. Say suppose mutation is essentially kind of introducing some particular gene in this human, who is extraordinarily brilliant or something. It is by generating those.
It may go otherwise also.
Yeah, it may go other way as well. But you have that selection operator, right?
Yeah. Then
which kinds of fine tunes only to get the gooder ones. I mean, better ones. So there, all those bad ones will get eliminated.
They will be eliminated.
Yeah.
Okay.
And just to note, like the previous one you told, the crossover, there is a limitation here in the sense for the selection operator to work, if you have more number of, like if you all have these good solutions, then you don't essentially need a selection operator. You should have a combination of good and bad solutions.
Mm-hmm.
So that essentially, mathematically speaking, you need to have a variance within, like higher variance.
But sometimes if this crossover probability choosing
Is wrong.
Wrong, if you choose wrongly,
Yes.
then the solution may oscillate.
Yes. But usually that oscillations won't be there that much. Like if you can see like this, you do not have, your population size is not just one. You have a much larger population, usually like 10, 50 or 80 or something like that, right?
Mm-hmm.
So this crossover probability, even if you choose low, when you have much larger population size, even in that population size, you can have individuals which are much better than others. As you go generation by generations, it will convert slowly, but you might actually get better results. Even if you choose a lower crossover. But if you choose very low probability, then okay, then what you essentially do is like you are kind of limiting your search space to whatever your initial guess is.
Yeah.
So then you might not get good solutions. You might converge to local optima, or you just will not converge at all.
So this PC should be always be more than 0.5, right?
No, it's like we usually choose something like 0.8 or something.
It should
0.7,
be high, yes.
0.8, something like that.
0.7 and above, yes.
Yeah.
And mutation should be
usually low. Like you can start with like 0.1 or something, but you can actually go, like the professor suggests, like going with 1 by n or something, where
Okay.
n is your number of, it depends on, if you have a much larger dimension, then preferably go with the lower mutation.
Okay, sir.
Yeah. You have anything else?
No, sir.
Yeah, fine.
Thank you, sir.
Yeah, thank you. So we'll just quickly go through one example, or else we can do, I have how much time? 10 minutes. I'll just go through some of the algorithm. So this is the next part of lecture in the third week, which we see the algorithmic view of how we are going to implement them in a computer. The first one is we'll start with the binary encoded generic algorithm. All these algorithms require a specific type of storage for your variable. So we'll start with something called a data structure, how your variables are actually stored in the computer. So when you have your population of say individuals from 1, 2, 3, so on up to n individuals, basically your population is one area. If this is your data structure, it has something called population, and inside the population you have something called individuals, and inside individuals you have something called chromosomes, and you have something called x-bin. X-binary is actually your actual value that you are going to store. So this is the basic structure we are going to use. Just to put it in a familiar way, like population has something called a parent. There are two different kinds of population. We have parent population and offspring population. Each one of them, parent or offspring, has something called individual. Individual is essentially your entire list of solutions within that given population. For each of the individual, you have something like objective function and some information regarding the fitness, like which kinds of takes inputs from both the objective function and the constraints. And then you have something called rank. If you're going with a different type of selection operator based on ranks, then you take the rank as input. Like depending on what you need during selection and other steps, you kind of decide what are the placeholders inside the individual. Now, as we discussed previously, these are the inputs for the encoding. The first one is population size. This you usually decide deciding among of your dimensionality of the problem. You decide this population size, and it also depends on the sensitivity. So if you have a function which is more sensitive, then it is more likely better to have a larger population. In the sense, you can have much higher diversity, so that the selection and other operators can work upon. The next parameter is your number of generations. This is essentially your closing criteria, which kind of tells you when you have to stop iteration. So the next one is your number of variables. You need to know what is the dimensionality of your particular problem. What you do is, the next step is you need to assign values to all these variables. So you start with a for loop over here, which says j equal to 1 to n. So you are basically iterating over the entire dimension of the problem. In the sense, if you have a variable of 8 dimensions, you are going from 1 to 8. For each dimension, you have to finalize what is the length of the chromosome. So depending on the precision, you decide, okay, this is the length of the chromosome I want, and then you know the variable bounds. Once you know the bounds of the, these are also kind of inputs that have to be given, and then you decide the inputs like this and here. This is for a binary encoded genetic algorithm. These are the only inputs you will be requiring for formulating the problem. Once you have this, the next step is to initialize the random population. So my population, this is the algorithm for that. You essentially go over, your first loop runs over I to n, where this is your population size. The second variable grows over small n is your variable dimension. The third loop goes over the chromosomal length. While initially assigning the values, like since it's a binary one, what you essentially do is, okay, you fix upon a length of chromosome. The next step is basically assign the bits to it. So you essentially go to each bit and decide whether you have to keep 0 or 1. And this has to be done randomly. Both 0 and 1 should be equally likely to occur. So what you do, you generate a random number from uniform distribution. If it is less than 0.5, you assign 0. If it is greater than 0.5, you assign 1. Depending, so you gradually do that for entire chromosome. And like this, you do for all the variables, and you do it for the entire population. Once you are done with initializing your random population, this is your xpin which we discussed previously. So once you have calculated your, you got all the strings, binary strings, you need to decode them to get the actual value of x. Decoding, which we previously discussed, you use the, how do you decode this? Decoding is essentially kind of a mapping from XL to XU. Maybe I'll use a different color. No, it's not visible. Yeah. So decoding is a kind of a mapping between, say you have some XL to XU. X is somewhere in between both of them. In binary space, you have something between 0 and 2 power L minus 1. So you are finding you have some variable here. So what you essentially want is to find a mapping between both of them. It's like dv equal to 2 power L minus 1 dv minus 0 by 2 power L minus 1 equal to x minus xl by xu minus xl. So once you have the binary string, you convert it into decimal value. That decimal value is this dv. Then you substitute into this formula, you get the value of x. And this x is what you will be storing in this particular value. This x is what we are going to use to evaluate the fitness function. The next step is to evaluate the population. Evaluate the population in the sense, get the fitness for all these values and store them in that corresponding placeholder. So what you do, you just iterate over the population, use the function f of x, evaluate the function, and then you iterate over each individual. This parent is a placeholder for that. In that individual of I, that function value could, sorry, 1 second. This for loop should be out of this. And you evaluate your population. Once you're done with it, once you evaluate the population, you'll go inside the loop. Inside the loop, what the first step is the selection. Selection, we start with the tournament selection. If it is a binary tournament selection, you just choose two variables, x1 and x2. And then if f of x1, the fitness value of x1 is less than x2, then you choose x1. Yeah, otherwise, you I mean, if x2 is less than x1, you choose x2. But if both x1 and x2 are equal, this is a case where you have to randomly select one of them. usually when you have functions which are of some nature like something like this, where essentially both x1 and x2 are having the same function value. These are some of the engineering functions will have these things where two possible solutions might give you the same objective function, like two possible designs will give you the same net cost of production or something like that. So if in your algorithm you should maintain that you are not preferentially giving weightage to only one of them. How do you do that is you essentially again generate a random number. If it is less than 0.5 you select the first one, otherwise the second one. So this is equivalent to saying you are selecting one of them with 50% probability. The next operator is your single point crossover. You can kind of extend it to multi-point as well. We'll just see what we do here is like for this the inputs are your parent pop, two individuals from the parent, two individuals these are my input, these are my output offsprings. Initially these values are anyway like it's a random bit, like it's an empty bit of length L and L. So first thing is you check, you generate a random number. R is a random number. You generate it from a uniform distribution 0, 1. Then next you compare it with the crossover probability. You compare it with the crossover probability and see if it is less than that. The next step is basically to identify the site. If you see the site is basically between 1 and Lj minus 1. So if you are having a string of length say Lj equal to 6, so you have consider this binary string. So whatever site you are choosing should be somewhere here. So you can only choose something 1, 2, 3, 4 or 5. You cannot choose 6. Basically if you are choosing 6, it is equivalent to saying I am not doing any crossover. So after you are choosing the random number between 1 and Lj minus 1, the next step is to actually perform the mutation, perform the crossover. So what we do is we have chosen some particular site. This particular site. Now we have two parents. So what you are doing, this is my P1 and this is my P2. So what you have to do is for the first up to this is my site. So what you have to do is first take this site, copy the same to the offspring. So like the first part of P1 goes as it is. This first part goes as it is to O1. That is the first step. Similarly for O2, you copy the first part of P2. This is essentially this. The next step is from site plus like from here from site, this is site plus 1 index. And from this index what you essentially do is copy it in the other way, like for the P1 you copy it into O2 and for P2 you copy it into O1. That is what we have written in the algorithm. If for suppose your random number generated is greater than PC, what we essentially do is extends both. So this is the crossover operator. Similarly, if you have a 2-point crossover, at this particular point here you have generated only one random number. What we are going to do is get two random numbers and use those two random numbers. Say if the two random numbers I am storing them as S1 and S2. What you will be doing here for k equal to 1 to S1, you copy P directly to O, and from S1 to S2 you copy Pi to OI. From S1 to S2 you copy Pi to OJ, and from S1 plus 1 and from S2 plus 1 till the length of chromosome, what you do is again do the same. You kind of copy Pi to OI. This is how you implement in the algorithmic way. So I think the time is over. Okay, we will conclude with this. The next week we will talk about how you do how do you implement algorithmically the mutation operators, and the various other kinds of operators we have discussed, how the selection of the other kinds of selection operators in the sense fitness, proportionate, and other algorithms. With this, we'll conclude the session for today. Yeah, thank you.
Thank you, sir.